Okay, so here's Unit 3. Unit 3 is EMR for short. You guys should have a little bit of experience with EMR. I believe it's taught in grade 8, so it's been a while. But at some point in your lives, in theory, you've learned a little bit about electromagnetic radiation. And I didn't teach you guys Physics 20. So whoever taught you Physics 20, you might have learned a little bit about stuff in Physics 20 as well. So I want to begin with something that hopefully you guys know, the speed of light. Maybe this is something you've heard of before. If not, let me tell you it for the first time. Okay. All electromagnetic radiation travels the speed of light, and this is a constant in our data booklet. It's 3 times 10 to the 8th meters per second. You may have used this before, maybe not, I'm not sure. And you might have used it in the universal wave equation, which is that V equals, this is the universal wave equation? Boy, I'm rusty. No, yeah, I do have it right. You guys ever used this formula before in Physics 20? V equals frequency times wavelength? Okay, we're going to utilize this a little bit in this section here, and I'll get to it when we need to. But you might have seen that the velocity of anything traveling the speed of light is this. Now, my goal today is basically an introductory section. There's no math. We're not doing any calculations yet. We're talking a little bit of theory, and we're just kind of working our way in. So it's a lot of pictures, a couple of scientists who you need to know their names of, and I got a couple of videos. Okay. The first thing I need to make sure you guys are aware of then is this spectrum here, and maybe you've seen this before. Okay. Electromagnetic radiation covers a vast array of things, from radio waves to microwaves to the infrared, visible light, ultraviolet, X-rays, and gamma rays. Is that something that like you've maybe heard of at some point? Okay. All of those things are technically radiation. Okay. Everything that has a short wavelength, basically at ultraviolet and further, these are dangerous to us. These cause health problems. And some of these you probably are aware of. For example, what can cause problems with ultraviolet rays? Do you guys know what the main cause of ultraviolet radiation is going to be? The sun. And if you get sunburns, you can get skin cancer. Yeah. Yeah. Skin cancer from UV radiation, not from UV. Okay. If any of you guys have ever been to the dentist and you need to get X-rays, they make you wear like the lead vest thing on top of you because X-rays can also cause cancer. And if you ever come into contact with gamma radiation, I don't know how this would occur, but maybe if a nuclear bomb goes off, same thing. Yeah, that's basically the idea behind the science fiction of the Hulk. Okay, not that the Hulk is actually real, but gamma rays are real. So, okay, a couple more terminologies I need you guys to know. Are you guys familiar with the term wavelength? Okay. In case you're not, let's do like the Cliff Notes review. Wavelength also comes up a lot in 30-1 math. Okay, I believe you guys are doing trig if you're in 30-1 right now. Perfect, great timing. So if you have a wave that looks like this, a wavelength, stay with me guys. A wavelength is how far it is from like crest to crest, or from like this point to this point. That's a wavelength. Okay, yeah, trough to trough. Okay, that's a wavelength. Okay, a wavelength then is a distance. And the distance is typically measured in meters, but because this spans so far, we could be talking something from the distance of a kilometer, like a radio wave is measured in kilometers, all the way down to X-rays, which are measured in like nanometers. Okay, it depends on how big the wave is. Now, not how tall the wave is. This right here is known as an amplitude. And amplitude increases the strength of something. For example, if we had visible light, for example, and the visible light was only this tall, that means the lights are pretty dim. But if we had the same wavelength, but it was much taller, that amplitude means that the intensity is bigger, and so it's a brighter light. Okay, but like by turning the light on brighter, it does not make the length stretch out more. Okay, the inverse or reciprocal of a wavelength is a frequency, and basically that's how many seconds it takes for it to like repeat itself. Malik. Yeah, technically you're right. Yeah, good point. Amplitude is technically half of that. Yeah. So amplitude is like from here to here. Yeah. I'm just meaning though, if you increase the amplitude and make it taller, that increases intensity though. Does that part make sense though? But you're right. Like the amplitude would be technically like from here to here, or from there to there. Okay. Whereas wavelength is side to side. Okay. Frequency then measured in hertz. Hertz's unit is like a, what is it? It's like a 1 over a second is the unit for it. It's a second to the -1. And it basically says, how long does it take for it to repeat itself? So this thing right here has a very high frequency because it's going up and down quite quickly. And this is a very low frequency because it's taking a long time. Okay. Oh, Philip, question. What's 1 over the wavelength? We don't actually have a unit for that because wavelength is measured, like wavelength is this symbol here, is measured in meters. Well, let's go back to this formula here. This formula here is what relates them. Its velocity is frequency times lambda. Oh, I think I get what you're saying. Because like frequency and period are related to each other, right? There's a formula that says that 1 over frequency equals period. Is that what you're thinking of? 1 over lambda. I don't know what formula you're talking about, honestly. It would be the reciprocal of wavelength, but I can't think of what formula you would have learned that in yet. So, I mean, yeah, I mean, that would be the reciprocal of it, but it doesn't really have a lot of meaning. The reciprocal of the frequency is the period, if that helps at all. So, I don't know. Let's talk more later. Maybe we'll figure out what you're thinking of. Okay, I need to pause for a second here. Back in the year 1907, give or take, I always forget the exact date, one of the most influential experiments in scientific history, and we'll have to know his name in our last unit. It's Ernest Rutherford. Do you guys know the Rutherford experiment? He did an experiment where he shot he shot particles at gold foil. And essentially he discovered the nucleus. And it fundamentally changed how we consider matter to be. Before that, there was a model of an atom where, guys, can you shush? It's distracting me. Where there was a positive nucleus. Actually, not even a nucleus, there was just a positive core, and there were negative electrons around it. And Rutherford came up with the idea of having atoms with a nucleus in the middle and having electrons literally orbiting around it. You guys maybe heard this story at some point before? Okay. Rutherford knew his theory was even wrong as soon as he proposed it. And here's one of the reasons why he knew his theory was wrong. Previous to him, James Maxwell had discovered something that basically says that whenever you have a charged particle moving, well, we learned this in our last unit. What happens when you have in a wire, let's say you have a wire, and in that wire, you have electrons, and electrons are going in that wire. What does it create around it? A magnetic field around it. But here's the thing. If a charged particle is constantly moving in motion and going around, it's constantly changing its acceleration. It's constantly changing like where it happens to be, like its location is changing. Maybe it even has a centripetal velocity or a centripetal acceleration due to it being in a circle. Okay? But literally as it starts and as it stops, as it begins to move, it's now going to have a magnetic field. Does that make sense? But we've also learned that what happens when you take a magnet, say you have a coil of wire that looked like this, and you take a magnet and you take a north and a south end and you shove the north end in. Doesn't moving a magnet also cause the electrons to like go through the wire as well? And so combining a whole bunch of principles together, Rutherford knew that if he had a particle, a charged particle, moving in a circle, it would then create a magnetic field. But the magnetic field would then create an electric field. And then the electric field would then create a magnetic field. And what he was discovering was this principle right here. Okay? This diagram is probably the best way that I can try to describe something. Is that what we actually have when EMR is going on is two simultaneous fields interacting with each other in kind of a sinusoidal wave. This wave right here is the electric field. This is an electric field going up and down, and then back up and down here. And as an electric field changes, it causes in this horizontal, like in this like perpendicular direction, a magnetic field to change. And that's basically the idea behind electromagnetic radiation, is that you have electromagnetic fields interacting with each other. So let me recap one more time here. When you have a charged particle moving, it literally creates a magnetic field. But when you change magnetic fields, it actually changes electric fields. But then when you change the electric fields, it changes magnetic, which changes electric, and it propagates. is often a word we use. Okay? And so this is often a picture that you're going to see referring to electromagnetic radiation. It's actually traveling this way. This is the direction that it's traveling, but the waves of the two fields are actually in the X, Y, and Z directions. They actually go in 3 different directions. The source, then, is an accelerated charge. So if I can go back to why I started this topic, Rutherford already knew that his model of the atom was flawed, because in theory, if you had a charged electron literally going around in circles, an electron going around in circles would then create a magnetic field. That magnetic field would create an electric field, which would create a magnetic field, which would create an electric field. And basically, he knew that this isn't true, because then all matter would give off radiation. And if all matter gave off radiation, we'd all be dead. So anyways, I don't know that you've heard this story before, but Rutherford actually knew his theory was wrong, almost instinctively. 2 years later, Bohr came around, and Bohr had a new theory of having a nucleus and having energy levels where electrons were in these orbits, so to speak, and there's like 2 electrons in the first energy level and 8 in the next. So, anyways, that's not what I want to talk about. I'm just giving context here. But I need you guys to know this. Accelerated charges is ultimately the source of EMR. That's actually what's happening in our light bulbs right now. We are getting light energy from our light bulbs. And the reason why is that electrons are literally being zapped from one side to the next, and they're being accelerated. As the electron accelerates, it creates a magnetic field, which creates an electric field, which creates a magnetic field, which creates an electric field, and it just keeps going on and on forever. And that's what makes this wavelength right here in different things there. So I need you guys to know a couple of scientists. Yeah, question? Sure, don't forget these are online too though, right? But sure, I'll leave it on here for a second. A couple of you guys have been asking me about knowing scientists. Yes, I really think you guys should know scientists. I'm not going to test you on it though until our last unit. Okay. In our last unit, I'm going to make you do a timeline where all of the scientists we've talked about through the entire year, I'd like you to kind of put them in order so that you kind of know who did what. Okay. So although I want to talk to you about some scientific contributions right now, don't stress about memorizing dates yet. So here's the guy I need you guys to know. It's James Maxwell. And maybe you've heard this name before. James Maxwell put together his theory of electromagnetism in 1865. Okay. And this is basically who he stole ideas from. Ørsted figured that current makes magnetics. And Faraday said that magnetics makes current. You guys kind of get the loop here? B leads to E, which then leads to B, which then leads to E. And they propagate each other. They create each other. And so here was his theory that Maxwell put together. First of all, how do you make EMR? You need an accelerating charge. Because an accelerating charge gives you an electric field. Okay. Secondly, the frequency at which that charge is moving is the frequency of the EMR being produced. Okay. Because remember, these charges are going to literally go from like here to here. They're going to go from a negative to a positive, and an electron is going to zip over here. And if it's alternating current, then it's going to zip back and forth and back and forth if you do AC current. The frequency at which you make a charge basically hop back and forth and back and forth and back and forth with AC current, that frequency matches this frequency right here. Okay. So how do you make gamma radiation? You take a charged particle and you make it zip back and forth like crazy. That's how you make gamma radiation. How do you make radio waves? Well, you make a charged particle zip back and forth, but maybe not quite so fast. Does that make sense? I'm actually going to show you a video of an experiment of the very first radio waves produced, and hopefully you'll be able to kind of see the idea here. So I got a video in a second I want to get to. Other things you need to know though. EMR travels the speed of light. Okay, I've already kind of discussed that. These waves are always perpendicular to each other. We're going to talk about words like refraction and interference later in the course. And then finally, this equation definitely applies still. So let me get to some of my videos and stuff. This slide right here just shows Maxwell's equations. We don't use these, by the way. But in case you're wondering, these are Maxwell's equations. We're not going to use them. So here is the experiment that kind of proved this. His name was Heinrich Hertz. And he performed basically the first radio wave. And rather than me try to demonstrate it, I got a video here I'm going to show you. So I'm going to hop over into here and find the video file, and hopefully this makes sense. Liam, can you do me a favor? Can you hit the lights for us just so you can see this better? I need to find the video on the Hertz experiment. All right. So what's happening here is, I'll let him talk. Sorry, it's a little hard to hear. Okay, so I'm going to fast forward because I won't show you the whole thing. But basically the idea is he hooks up electricity so that a spark goes back and forth here. The frequency at which the spark goes right here determines the frequency of this wave right here. And what ended up happening is it sent a signal, and now a spark kind of shows up over here. Okay, so I'm going to fast forward here to where he does this a little bit better. We'll watch this experiment. Okay, so what he's done is he's hooked it up so that there's going to be charge now going through this, and hopefully you guys will see there's a little spark between here and here. He set up a receiver over here, and this receiver has a light bulb on it. And the light bulb should not light up normally, right? But as he sends the spark between these two pieces right here, a signal is sent to these two right here, causing electricity to go through here. And you'll see this little light bulb light up. So I'll just rewind it a little bit so you can watch. So look for the spark right here and the light there. You can't actually see, oh, there it was. You can see the spark right here, hitting that one as well. Could you guys see that? Should I rewind it one more time? So what you're looking for is right here, between these two things right here, there's electrons jumping from one to the other. Those electrons jumping here is causing a signal to be sent over here, and electrons are running through this current here, causing this little lamp to light up. So watch the spark and the lamp happen simultaneously. This is a signal. You guys see that? Spark, lamp at the same time. Here, one more time. So I can't really see the spark in between there anymore. But does that kind of make sense at all? Oh, it literally, as I froze it, you can see it. Isn't that cool? Okay. This is the first known experiment where basically electromagnetic waves were being used. Okay. In a way, it's almost like a radio wave was being sent. And I've got that picture right here. That's what apparatus does. When you're sending out a radio wave, it sends out a signal, and that signal is then picked up by an antenna. Okay? That's Heinrich Hertz. Okay? What I want to show you next is a video that talks about how scientists calculated the speed of light. We believe the speed of light to be 3 times 10 to the 8 meters per second. I'd like to show you a video explaining how some scientists figured that out. So here's a second video I'm going to show you here. This is known as measuring the speed of light.
Lantern awoke the model apart.
Okay, just pause for a second there. So here's Galileo's experiment in case it didn't make sense. People on mountaintops with lanterns. I light my lantern, and as soon as the person on the other mountaintops sees the lantern from mine being lit, then he lights his. Okay? So basically, it would be like, I put up my hand. As soon as you see me put up my hand, you put up your hand. And then we measured how long it took for that to happen. That's time. We then measured the distance between them. Distance divided by time gives you velocity. The biggest problem with that, though, is that most of the issue is not about how long it takes light to travel, because light travels almost instantly, right? It's really about the people's reaction time. So Galileo made a valiant attempt at it, but the reaction time's too slow. So here's some more people who did experiments. Okay, so this next guy, he basically measured distances, and maybe if I can go back a little bit of a slide here, no, a little bit further back. This picture, right there. He was trying to measure basically where the Earth was compared to where this moon of Jupiter's was. And he was trying to measure basically the distance that it traveled here to here and here to here for light. He was trying to calculate distances that way. A little bit better than on top of mountains, because since it's traveling further, he had a little bit more reaction time to try to figure this out. Literally, this would take like days or months apart, right, as the Earth moved, as he's trying to make measurements. So I don't know exactly how he did all of it, but basically the story is he used the moon of Io to try to calculate it, and he got this value here. Close, because 300,000 kilometers per second, if you add 3 more zeros, that's 3 times 10 to the 8. So let me keep going here, though. Okay, so if that doesn't make sense, maybe I can try to describe the picture better. He shot some light from here to a mirror, and then the light would, in theory, bounce off of the mirror back at you, and you'd measure it. But he had this wheel rotating, and so sometimes the light could go through the gaps in the wheel, and sometimes it wouldn't. What he did is he altered as the thing rotated the speed of it. And so sometimes the light would go all the way through and come back, and it would hit one of the spokes, and you wouldn't be able to get a measurement. But if he sped it up a little bit, by the time it went all the way here and all the way back, maybe it would fit through a seam. And by doing that, he tried to calculate the speed of light. Okay. Not a bad idea. A little bit high. Okay, this is the actual speed of light to the best of our ability to measure, but we always round it to 3.00 times 10 to the 8. Okay, if this is in kilometers, can you guys kind of imagine you got to move it 1, 2, 3, 4, 5, 6, 7, 8. So this is what we believe the actual speed of light to be. Okay, that video showed you a couple of really basic experiments that tried to calculate the speed of light. What I would like to do on the next slide right here is show you an experiment I need you guys to know. It's called the Michelson experiment, and it is highly likely that this is going to show up at some point. Okay, I've actually done all the math on here, so let me see if I can describe how he did his experiment. This is one of the most successful ones in history. He had a telescope, and he had a mountain, and he kind of put them like really far apart. The telescope and the mountain were like miles apart. Okay. He shot a beam of light, in theory, at a set of mirrors. Okay. And as the mirrors go, they're going to rotate like around in circles like this. And ideally what happens is the light hits the mirror, it goes down, it hits this mirror, it bounces back up, hits the other side of this mirror, and he measures it over here. And what he's trying to do is make it so that it travels a very long distance. In theory, it went 35 kilometers down and 35 kilometers up, more or less. Technically, this is on a hypotenuse, so I know he did a little bit more math than I'm showing you here, but more or less, it's 35 kilometers up and down, or whatever that number is there. I can't see that number well. Is it 35? Okay. Right. So he shoots it all the way down, all the way back up. Now, here's the thing. As this disk rotates, in the time it takes this light to go all the way down and all the way back up, it's been rotating. And so let's say it rotates exactly 1/8 of a rotation. It would then hit in exactly the right spot to go like that. But what if the octagon was actually slightly in the wrong spot? It would actually cause the light to hit it here and bounce the wrong way. And so what he did is he varied the speed of this thing's rotation, and he discovered that if he set it to 533 hertz, light that was shone here would deflect down, come back up, and he would still be able to see it. If he set it to 534 hertz or 535 hertz, and it was spinning too fast, he wouldn't get a measurement because it wouldn't have rotated the proper amount. Does that make sense? So by getting a hertz amount, he used this formula here to get a period, and that told him how long it must have taken for the light to go all the way down and all the way back. He now has a length of time. But that frequency is how long it takes the wheel to turn all the way around. But there are 8 sides to this thing, so that's why there's a 1/8 ratio there, is that it took that long for it to go all the way around. For it to make 1/8 of a rotation, he took his answer and divided by 8. That was the amount of time it takes for it to go all the way down, all the way back up, and have this rotate 1/8. And then finally he took his distance, which would have been 35 and 35 for 70, converted it into meters, divided the two, and that's how we got the speed of light that we currently have. It is very plausible that they're going to give you a question similar to this, or I'll even give you some practice ones like this. So the way you solve it is you take your frequency, that's a given, you turn it into a period, you divide this period by however many sides are on the shape. So if it's an octagon, divide by 8. If it was a triangle, divide by 3, I guess. And then take distance and time and divide them by each other to get a speed of light. Does that make sense? Okay. Okay, a couple more things I want to talk about. I want to finish up my lesson pretty quick here today. I'm going longer than I wanted. These are some topics that we will eventually talk about. Okay? We're going to get to these one at a time. We're going to talk about how to detect EMR. There's directly detecting it and indirectly detecting it. Sometimes you have a signal that is completely unimpeded. Like, for example, your cell phone right now is picking up EMR. There's a satellite overhead, or it's actually not from a satellite, it's probably from a radio tower overhead that's sending a 4G or 3G signal to your phone, and it's just directly going to your phone, right? That's unimpeded. But we can have things reflect or transmit as well, and so it can go indirectly. For example, light can bounce off of objects, like if you have a mirror. Okay, I want to show a quick video clip of the Big Bang Theory. Maybe you've seen this episode. This is where they're going to try to calculate the speed of light in a similar experiment where they're going to reflect something off the moon. This is my last video, I think. Maybe you've seen this pretty clip they had. As long as it gets. So they're shooting a laser. It's hitting the moon and coming back, right? Okay, so how are they calculating the speed of light? They know the distance from here to the moon and back, right? That's been calculated. And then they calculated how long it took the laser to go from here to the moon and back, and just did distance divided by distance divided by time, right? And apparently it takes 2.5 seconds to go from here and there and back. Does that make sense? So that's a modern experiment then for how you try to calculate the speed of light. So, anyways, move forward here. We want to talk about light a little bit more. I'm kind of introducing some concepts we're going to get to later. There's actually a couple of different models for how people thought of light. Some people think of light as being a particle, and some think of light as being a wave. And we're going to discuss more of those over the next little while in our course. I like this diagram here. I don't know whether you guys see the P-A-R-T-I-C-L-E or W-A-V-E. But we're eventually going to discuss some pretty weird principles of light, in that light can actually act as both a light particle and as a wave. We're going to get to that in the last chapter. But I want to tell you about some more scientists who did some experiments with light. Okay, let's start with Sir Isaac Newton. Sir Isaac Newton believed that light was like a particle. And the reason why is probably most likely due to this one right here. Light can be reflected. He knew that you could bounce light off of a mirror. And he thought, well, you know what else bounces? A ball can bounce off a wall, so maybe light is kind of like a particle. Maybe there's actually like a particle element to it that it can bounce off of things. And that was Isaac Newton's theory. And for many, many years, because he was like Sir Isaac Newton, chair at Cambridge, nobody challenged him. And so everybody in the scientific community said, Newton thinks it's a particle. Okay, light is a particle. It wasn't until after he died that some other scientists started to think, well, maybe light behaves more in these wave-type patterns. So here's a name I want you guys to know. His name was Grimaldi, and he discovered that when you put light through openings, they wasn't perfectly sharp. There was some fuzziness around the edges. I don't know how to describe that, but like imagine that I was trying to draw like a straight line like this, and like I want it to be a shadow. It was a little bit like iffy around the edges, especially when I zoomed in. Here's what that implied to him. It implied that the light didn't actually go in a straight line, but it actually went like in a back and forth pattern. And so when it went back and forth and back and forth and back and forth, it wasn't a crisp edge to it, but there was a little bit of fuzziness. He kind of thought, well, maybe it's a wave. Okay. Another guy, Simeon Poisson, this is a funny story here. He predicted that light should not be able to go in these wave patterns around a disk. And so he made a prediction that you should never have a bright spot. Later, another guy found this, and he named it after the first guy to, like, make fun of him. It was like the ultimate, like, I don't know, throwing shade at somebody. Here's the idea, basically. Okay. The one guy predicted that you would never have this bright spot in the middle. But because we think that light now goes according to waves, waves can actually bend around corners here. And they can actually meet up in the middle here, and you can actually see this little bit of light right here in the middle. So Poisson figured, no, that's never possible. And when, what's his name, Arago eventually found it, he named it after his buddy just to make fun of him because he was wrong. So this is actually evidence that light can actually bend around an object due to wave-like properties. We're going to talk more about this in the course. If it doesn't really make sense right now, that's fine. Like I'm doing an intro day today. So here's another scientist. His name was Huygens. He's a Dutch scientist. And what he figured out is that when light hits something like, say, a body of water, some light gets reflected, some light goes through and gets refracted. And he discovered that if you had 100% light over here, say that 20% of it made it through, he discovered that 80% of it actually was reflected. And these two numbers here added back up to 100 again. And so he kind of figured, well, maybe this wave can literally be split into two pieces. So maybe light isn't a particle. Okay. Later on, we're going to talk about something called wave-particle duality and some really crazy quantum stuff. And we've actually discovered, we'll get to this later, that light is actually both a particle and a wave at the same time, depending on whether you're observing it or not. And it's some really crazy quantum stuff. But we'll get there later. So, okay. That's actually the last experiment. We're going to do this in topic 7. It's called the double slit experiment. And why don't I just let you guys read this later, because we're going to talk about this in topic 7, but he actually discovered some really weird principles, that light was going through in wave fronts like this. And this light right here, you would think light was supposed to hit this screen right here and never go through. And he actually got this really weird pattern. I'm going to show you guys this in a lab one day. So, okay. We're going to eventually talk about a guy named Max Planck. And he came up with the idea of quantum theory. And Albert Einstein actually posited the idea of something called a photon, which is where light is actually a particle. Maybe you've heard that phrase before, like fire the photon torpedoes, like in Star Trek or something. A photon is actually believed to be a light particle. Okay? And again, I don't expect this to make sense to you right this second. Okay? I just want to introduce some concepts to you. These are words we're going to use later on in the course. But yeah, Einstein figured maybe there's actually a photon of light. Okay. Oh, here's where I want to finish, because I want to be done talking today so you have a little bit of time to work on things. What I need you guys to take away from today's class is that you know a little bit, like an introductory stuff about EMR. And I need you guys to know the different sections of EMR, basically like the spectrum. So I've got some notes here that I don't need you to memorize, but you definitely need to know the order, okay? The longest wavelengths we have are either low frequency AC current or basically radio waves. Radio waves are the biggest waves we have. And working forward from them, after radio waves are microwaves. After microwaves are infrared rays. After infrared is visible light from the sun. These are the only waves that we as humans can actually see. The rest of them are invisible to us. Everything after visible light causes health problems. So that's your ultraviolet waves, your X-rays, your gamma rays, and cosmic rays. Okay. And so basically, if you were to draw a picture, radio waves are the longest, and as we get smaller and smaller and more condensed, yeah, cosmic rays we don't even have on Earth. Like, they are so infinitely squished together that, like, they, yeah. Interesting, actually. They are high doses, but they're not dangerous to us because it actually will literally phase through matter. I have no idea. That's a good question to research. Okay. So long story short, if I give you a picture like this, way at the very, very beginning of our notes here, are you guys somewhat familiar with these terms? Infrared, visible light, ultraviolet, X-rays, and gamma. Can you put them in order? Okay. I've seen diploma questions where they ask you to basically put them in the right order. Okay. That's all I want you guys to get out of today. Everything else that I kind of talked around, we're going to spend much more time in detail talking about. This is just kind of like get us going. Okay, I think that's about it for my notes, right? Is that where it finishes? Okay, I have one more video that's like an hour long. We're not going to watch it. But if you would like to, this is totally optional, and you want to watch a video talking more about the different parts of the electromagnetic spectrum, I put it on my website. But it's an hour. So unless you have a free hour of your life and you really want to know more about X-rays or more about gamma rays or cosmic rays, you guys can. But I'll leave it to you guys. It's on my website. Okay, I'm done now.